As climate change becomes an issue that is ever increasing in its importance, the topic of energy efficiency has become a common one in the discussion of dwelling construction. How can we make our homes less reliant on energy? How can we naturally cool our homes in the summer? And conversely, how do we naturally heat our homes during the winter? In this presentation, we will discuss the following: the methods used in analyzing energy efficiency in Australia, the usage of known methods to increase energy efficiency, and how First Rate 5, an approved energy efficiency analysis software, can showcase how altering some parts of a house will affect overall energy efficiency. When you're building a house, the National Construction Code requires you to meet a specific energy efficiency benchmark as defined by the Nationwide House Energy Rating Scheme, or NatHERS for short. NatHERS provides a star rating, which is indicative of how efficient the dwelling is in terms of energy consumption for heating and cooling. For all of Australia, bar the Northern Territory, an energy efficiency rating of 6 stars is the minimum requirement for newly constructed houses. Star ratings start from 0 and go to a limit of 10. The higher the star rating, the more energy efficient the house is. However, applying a blanket energy benchmark across the entirety of Australia may seem a little unfair. Melbourne is much colder in the winter, and it wouldn't be a surprise if they required more heating. The inverse is true for areas in the northern regions of Australia. To account for this, NatHERS has introduced climate zones that take into account both temperatures and meteorological characteristics of certain areas to determine the maximum heating and cooling energy levels for certain regions. Each region has been labelled with a number that can be referred to when determining maximum heating and energy cooling limits. The main cities of Australia have been included as an example. As mentioned previously, the NatHERS climate zones delineate the maximum heating and cooling energy limits for certain areas. In this slide, we use the example of a slab-on-ground construction and observe the associated maximum energy loads for Climate Zone 13, which is where Perth is situated. Here we can see the maximum heating load is 57 megajoules per meter squared per annum, whilst the maximum cooling load is 39 megajoules per meter squared per annum. The differences between maximum total and maximum heating and cooling will be explained in the oncoming slides. Note that the Northern Territory and Darwin uses the energy limits as specified in BCA 2009, explaining the extremely high maximum total energy load. Furthermore, New South Wales uses its own measure for energy efficiency, BASIX, which is a different set of requirements but is accepted by NatHERS. We will briefly discuss this in the next slide. The Building Sustainability Index, or BASIX, identifies design features that affect the level of energy consumption and water use in newly built houses or recently renovated homes. For New South Wales, BASIX governs the energy limits instead of NatHERS. The BASIX thermal comfort climate zones replace the climate zones used by NatHERS, and similarly, the maximum energy load would also be slightly different. More information can be found on the BASIX website. For your home to be NatHERS compliant, it must have cooling and heating energy loads below the maximum specified amount for your NatHERS climate zone. In addition to this, the combined energy loads from both heating and cooling must fall below the total maximum energy allowance. Here, as the cooling load will fail, the dwelling will fail to comply to the NatHERS requirements. The R value is the thermal resistance of a material, and thus it acts to slow the effects of temperature change. An R value is determined by the formula given, the thickness of the material in question divided by the thermal conductivity of the material. As brick has a relatively high R value and associated thermal mass, it exhibits the ability to regulate temperature throughout the diurnal cycle. Below is a table from the National Construction Code that summarizes the thermal conductivity of walling materials. These values are used to calculate the respective R values of your constructions. The thermal conductivity of bricks have been highlighted as shown. A common question in the masonry industry is how the R value changes for composite materials. In this case, the solution is additive. Simply calculate the R values for each different material and then add them together for the final R value. The following example showcases this. Consider a double brick cavity wall with a 40mm air gap. We know that the width of a standard brick is 110mm. Assuming a 3.75 kg brick, it will have a thermal conductivity of 0.65 watts per meter Kelvin. The R value, as mentioned previously, is the thickness divided by the thermal conductivity. The calculated R value for the brick leaf will then be 0.11 divided by 0.65, giving us 0.17. For the R value of a 40mm airspace that is non-reflective and unventilated, the NCC states that it will exhibit an R value of 0.17. The total R value will then be the summation of all three materials, including brick twice, once for each wall that we have. This gives us 0.17 plus 0.17 plus 0.17, and so the total R value is 0.51 meters squared Kelvin per watt. An interesting note is that despite the air gap being almost a third the width of a brick, it provides the same R value. Air, as it turns out, is a very good thermal insulator. In this following section, we will address the primary factors affecting energy efficiency. These include thermal mass, orientation of the dwelling, insulation, and shading. Do note that these factors are not exclusive. There are many other attributing factors to increasing energy efficiency. Thermal mass is the property of a material to store and release energy. Using the idea of thermal lag, that is, the delay in time for the effects of heat and cold to become apparent through a material, thermal mass can assist in regulating internal temperatures throughout the day, absorbing heat in the day to release it at night when it is cooler. Some materials with high thermal mass include brick, stone, concrete, and even water, as it can be used in water walls. Do note, however, materials with high thermal mass may have adverse effects in climates that have a constant temperature. In a warmer climate, you will absorb heat when it's warm, only to release it later when it is still warm. Thermal mass is an often overlooked factor in designing for energy efficiency. House orientation refers to how a dwelling is positioned, and if it is optimal in utilizing climatic features to increase energy efficiency. Some examples of proper house orientation are positioning windows to catch the sun on colder winter mornings, or inversely, positioning the windows to the north so you can catch a more consistent amount of heat and light throughout the day. Even positioning hallways to allow for an east-west wind may also increase cooling efficiency. Do note that the arrangement of rooms within the layout of a house will also greatly affect the energy efficiency of the dwelling. Insulation is one of the most desired traits when considering factors for increasing energy efficiency, as it has the ability to stop heat, both from entering the home during the summer and from escaping the home during the winter. There are many options for insulation, like bulk, reflective, and composite, all with varying properties and cost. Although insulation remains to be a crucial component, it is an often overstated factor in determining energy efficiency. Shading employs eaves, awnings, and other methods to either block out or mitigate sunlight striking the dwelling, effectively reducing some heating effects. Beware that improper shading, like blocking out the sun on a winter day, will result in more artificial heating required and a reduction in overall energy efficiency. To reiterate, we have just gone through the certain design considerations that are required in improving the energy efficiency of a dwelling. We do this as to comply with the required 6-star energy rating as defined by NatHERS. Now we will see exactly how these design considerations play a part in improving energy efficiency in a build using FirstRate 5, a NatHERS certified software used to rate energy efficiency. To observe the effects of thermal mass and materials, this model house was created in FirstRate 5 using different walling materials and then analyzed. Keeping all other factors equal, the star rating of each type of construction is as follows. The following slides will translate these ratings into differences in internal temperatures during both summer and winter. In the simulation, a brick cavity wall in the summer can make a household 11 degrees cooler when comparing the peak external and internal temperatures. Conversely, the same wall can make the internal temperatures of a dwelling up to 14 degrees warmer in the winter. It's no wonder why double brick cavity walls have the highest NatHERS star rating. In a weatherboard construction, the simulation shows us that the summer temperature differential is 7 degrees Celsius, whilst the winter differential will be 12 degrees Celsius. It is clear to see that the materials used in the construction of a dwelling will have notable effects on thermal comfort. As you can see, material choice is a critical component in increasing energy efficiency. In both hot and cold climates, a brick cavity wall will exhibit more favorable internal temperatures when compared to a weatherboard wall. To observe the effects of house orientation, we will leave all other factors equal but change the facing of the house. The plan view below shows a typical north facing, and this gives us an Energy Star rating of 7. By changing the direction of facing to west and east, we achieve a rating of 6.8 and 7.4 respectively. This discrepancy is notable. A change of 0.6 between maximum and minimum energy ratings can easily determine whether or not your dwelling fails the energy efficiency standard. Now let's analyze the effects of shading. In this control model, a large eave covers the patio and a smaller eave covers the front door. Both of these can be seen in the plan view of the house. The energy efficiency rating that First Rate 5 gives us is 7.1. Keeping everything else equal, we now apply eaves on the east and west walls of the house. The provided shading increases the energy efficiency rating to 7.4. If we think about this, it makes sense. The eaves block out the sunlight during the morning and the afternoon, reducing the amount of energy required to cool the house at these times. What would happen, however, if we were to put eaves on the north and south sides of the house? The star rating will be slightly reduced to a value of 7. The eaves are not properly positioned to block the harsh summer sun, and they also make the house unnecessarily cool in the winter, thus increasing artificial heating. From this example, it can be seen that improper installation of shading will have negative effects on energy efficiency. Additional information on energy efficiency can be found in the technical section of our website. If you're interested in energy efficiency, I would highly suggest checking out the Sustainability and Energy Efficiency Manual, as it covers much of what I have said today and even more. The Association offers a wide range of free resources available to the public, such as technical manuals, research papers, and case studies. The Association also has a technical hotline where we can answer any of your brick or block related inquiries. Should you have any questions about the design and construction of brick or blocks, please feel free to give us a call on the technical hotline. This concludes today's presentation on energy efficiency. Thank you for your time, and we hope you enjoyed today's presentation.